Yeah, welcome back. Let's thank Dr. Gilles Bellon from CNRM Toulouse in France for agreeing to offer a lecture on convection-circulation interactions.
Good morning. So today's lecture is about the interaction between convection and circulation, and especially different conceptual ideas that people who work in this field try to apply to make sense of the interaction, or maybe more of circulation or more convection, making sense of one of the aspects so that they would be able to treat the interaction a little more easily. So we'll be talking about large scales, right? So large mesoscale and higher, let's say synoptic and large scale. So these types of systems, rather than things that are more mesoscale or more the convective scale. And all those modes of organization that you've seen already, you've seen this type of diagrams before in Maxime Stoke and Professor Srinivasan Stoke as well. So you have those large systems that result in largely, or at least in part, from the interaction between convection and circulation. And so the question is, what is our conceptual understanding of this interaction that we can apply across scales to these phenomena? And so, well, if we go back to the equations or the physics, where does it really appear? Where does convection appear? Where does dynamics appear? If we go back to the primitive equations that you have here, well, you can see that you have all those diabatic terms and all those terms in the humidity budget, and even this term here in the momentum budget, the horizontal momentum budget. And both the effect on humidity and temperature lead via the hydrostatic approximation to an effect on the dynamics via the gradient of geopotential. And convection actually will contribute to all of those diabatic terms. So while latent heat comes, of course, from condensation in convection, but then you have convective clouds that have a radiative effect, and then you have mixing by the convective circulations, so that we consider small scale when we think of large scale motions and phenomena. And so those three terms will be impacted by convection. Same for the terms in the moisture budget, where you'll have the condensation again, and then the vertical mixing by small scales, and some of these motions are convective. And then even in the convective momentum itself, we're going to have also mixing, and the convective momentum transport has been shown to be quite significant in some cases. But the main terms are really the diabatic ones, because the buoyancy that appears here, or the density temperature, varies mostly with temperature, and so the diabatic heating is going to be the key factor. And we have an idea of what kind of clouds, what kind of diabatic heating profiles you can expect from different types of clouds. It's a vague idea. There's a lot of variability within each cloud type category, so it's more illustrative than prescriptive, this figure. So you have the boundary layer clouds here, and then you have the deeper convective clouds. And you can see that the diabatic heating is dominated by the convective heating in blue here, the mixing being in light blue, and the radiation term being in red. So there is essentially one order of magnitude between the latent heating and the other terms. Doesn't mean that they are not significant. As I said yesterday, if you take a a cloud ensemble and you want to so have an idea of what the radiative heating from the clouds is, you can take about 15% of the latent heating, and that's a good approximation for your radiative heating, especially at intrasonal scales. So if we know these terms, actually, we have a system that's completely closed, right? So if we can figure that out, we have something that's completely integrable numerically. And also, if we don't have those terms, and if we just keep the friction at the surface, we would not have any motion, right? So convection, by its contribution to the diabatic terms, is actually very important in maintaining atmospheric circulation. If we look at it geographically, you can see also that the atmospheric latent heating, that's essentially proportional to the precipitation, is really in the regions of convection. And the same thing for the radiative heating. You have actually a very large signal of the clouds themselves and also of the humidity that's around the clouds. Now, if you look at it the other way, how does the circulation act on convection? The main element here is probably going to be vertical transport, because that's where we have large gradients of both humidity and temperature. And so if you have ascending or descending motion, that's going to restratify the atmosphere, and that will have an impact on both CAPE and SIN, those two quantities that control, in large part at least, the occurrence of convection, if we're talking about the convective inhibition, and then the convective available potential energy is going to control to some extent the intensity of storms. We'll get back to how much there is of it and how relevant that is. CAPE is a sort of upper limit on what the available energy is, because it's computed from a moist adiabat rather than what we would have in a cloud that would be more of an untraining moist adiabat. So if you have ascending motion, you will bring moist air from the surface up, so you're moistening, but you're also taking air that has a little potential energy up, and that's going to be the factor that's most important for the potential temperature. Even though the surface area is warmer, it has no potential energy, so when you bring it up, it actually cools, and it's cooler than what you have above. So you're actually cooling and moistening the free troposphere, which makes it less stable and moister. So that's very favorable for convection. You actually, essentially what you're doing is building CAPE when you're doing that. And also, you're also making sure that entrainment won't be as efficient as at drying the updrafts. And so it's going to maintain their buoyancy better, and they'll be able to go further up. So those two are quite conducive to more convection or convection in general. And if you have subsiding motion, you're doing essentially the reverse in the free troposphere. There's also the effect right at the top of the Bombay layer that can be very important, because that's where you're going to have, an inversion. And if you have subsidence pushing on an inversion where you have a very large gradient of potential temperature and humidity, so of buoyancy, you're going to build up SIN quite efficiently with that advection, with that transport. So vertical transport is definitely the largest term. And it shows, when you look at just the distribution of beams of vertical velocity. So the negative here is ascending motion, positive here is this subsiding motion, because it's omega, it's in pressure coordinates. And here you have the SST. So that's the PDF of omega 500 and SST. And that's the mean clouds you have in all those different bins. And so middle clouds, you can see there is a little bit of an influence of SST. But then when you look at the high clouds, those horizontal lines essentially are saying that there is absolutely no sensitivity to SST. That's completely true up to fairly large ascending motions, right? So what's going to control the existence of clouds and precipitation as well is going to be really the large scale motion. So in both ways, in inhibiting convection when it's subsiding and enhancing convection when it's ascending. Okay, and we would think that the SST is a fairly large control on convection, but vertical motion is much more. All right, this is not to mean that we should really completely neglect horizontal advection. So you've seen yesterday that sometimes we use moist static energy as a variable. When you look at the vertical advection of moist static energy, so it's proportional to the gross moist stability, which is small. And most of the time it's positive and small. In average, it's positive and small, but it happens sometimes to be slightly negative. And so that just means that the vertical advection of energy itself is very small. The advection of dry energy compensates the vertical advection of humidity. And so what's going to happen is that if you want to look at the energetics of a mode, vertical advection won't be that big a term. It's going to be more efficient to influence convection itself than maybe the growth of a mode or something like that. And then you can look into it and see that horizontal advection then provides some of the energy or removes some of the energy. So we had the case yesterday in Shugwang's talk or Shugwang's lecture where he had advection of humidity, horizontal advection of humidity that was important in the instability of his mode and of his moisture mode. And you could see also that the zonal advection was a negative term that was compensated by the influence of winds on surface fluxes, while the meridional advection was a positive term. Talking about the influence of surface winds. So if you have more winds, you have more fluxes at the surface. Because if you just take the simplest model we have for fluxes, you have the flux of any variable that's going to be equal to the density, then the speed of the wind at the surface, and then a coefficient, so drag coefficients, and then the difference of that variable x between the water at the surface and the atmosphere at the surface. Okay? So if you increase just the speed of the wind, you increase the surface fluxes. If you decrease the speed of the wind, you decrease the surface fluxes. And so that will also essentially move, instead of moving the environment line that's in red here, as the vertical advection does, it's going to change the black line, moving it up or down, depending if you add moisture and humidity to the boundary layer, or if you remove some, or if you don't add as much with the surface. All right, so we've got those physical effects, but it's hard to figure out what happens overall with those effects and how we can think of what happens with convection and how the dynamics are going to respond to it, or what happens with the dynamics in response to convection, and that is going to condition the circulation. So after this fairly long introduction, this is the aim of this lecture, to see the different theories that have been come up over the years, and and how valid they are, and see 4 of them mostly. So convective instability of the second CAM, convective quasi-equilibrium, self-organized criticality, and then a weak temperature gradient. And historically, the first one was the convective instability of the second kind. And it came from the observation that convection is fed by moisture convergence. And so the idea was that we could just model precipitation like moisture convergence, or a large fraction of it. So we look at the column moisture convergence, and the precipitation is just going to be that, or proportional to that. So mathematically, that's how you can write it. And I think the idea was that it could be used for parametrization. So the QO parametrization of convection was based on that, for example. And so there was one big success of this idea, which was it could explain the convexly coupled equatorial gravity waves. Essentially, I said yesterday that the convexly coupled gravity waves are just a sort of limit case where we can neglect the storage of humidity. And what happens if you just decide that all of the convergence of humidity is consumed by precipitation, that means there is little storage of humidity in the column, right? Well, you have the surface fluxes, but it limits how much humidity you can store. And so you will be able to essentially have modes with little storage of humidity that are represented. And so this is the limit case that we were talking about yesterday. Now, I think by the mid-80s, this idea was completely forgotten. Well, because there was that missing link between really convection. It was essentially the large can was controlling convection too much. That systematic link wasn't giving space for an actual interaction. You had the dynamics that were essentially constraining the dynamics directly through that systematic link here. And so you wouldn't have any moisture storage except for evaporation, which is somewhat strange because you need convection to bring that evaporation up, right? And you don't have those processes anymore. Well, there was no question of moisture modes at the time, but it's clear that this type of approximation can't give you moisture modes at all, because moisture modes are modes for which the storage of humidity and the advection of humidity are super important. It would also have this weird behavior where, in terms of scale selections of waves, it would select the smallest scale, both in time and space. And so it would yield to some weird behaviors of the parameterization that were based on that, and on that type of formulation, like the QO parametrization, where you would tend to have point grid storms, which is essentially a storm that develops in only one grid point of the model and becomes super, super intense. And so there are quite a lot of references here, and you see that the latest one is 1974. And so it's an interesting idea to keep in mind that you have those two processes, diabatic processes and convection in particular. And on the other side, you have the dynamics. And if you tend to couple them a little too closely, a little too systematically, you run into trouble. So the next idea came up first in Arakawa Schubert's paper, which was aiming at parameterizing convection in a general circulation model. And maybe the most important paper on that is a sort of review that Emmanuel Neely and Bresenden wrote in 1994. The basic idea is that you have negligible inhibition, convective inhibition over the oceans. And so, over the tropical oceans. And so that means that convection happens maybe sporadically, but in a regular form. And it will happen, it will occur pretty much everywhere over the tropical oceans at all times. Second assumption is that convection is a very fast process compared to all other processes. And that means that any instability is going to be consumed very fast. So let's say instantaneously, if you compare to the time scales of interest for the dynamics, let's say in less than a day, a few hours. So that means that there won't be any cape anywhere. So no scene, no cape in the most radical version of the theory. Now, of course, when we think about actual convection, it never completely consumes capes because it's not the most adiabat, that's a reference. So if you were to define an entraining cape, it would be probably more appropriate, except that we don't exactly know what the entrainment is and it varies in different situations. So it's not as easy to define as just cape. So this gives us a very simple image of convection, where you have any kind of large scale. It can be surface fluxes, it can be vertical advection or circulation in general, advecting humidity and temperature. If it creates any instability, then that's consumed by convection and removed. So that means that our free tropospheric profile of buoyancy, at least, but we can assume that that applies both to humidity and temperature, that's tied to the boundary layer temperature and humidity through the most adiabat or the reference profile that we choose. Arakawa Schubert actually talked just about a reference profile rather than a most adiabat. So how does that work? So imagine you have a vertical gradient of temperature like that. That's already at that reference profile as a function of temperature and humidity in the boundary layer. Now, if you add a large scale forcing, let's say if you add only the large scale forcing, your new profile after delta T would be this light blue one here. But it will never get there because the convection is going to react almost instantly. And it will essentially get this profile back to a reference profile, but that will be maybe with different humidity and temperature at the bottom, okay? So essentially redistributing the temperature, the energy and humidity on the vertical so that you are at the reference profile with maybe a different state in the boundary layer. So it's a little bit difficult to do because you have to recompute these, the evolution of the boundary layer values and at the same time the profile. So for that, and thinking of the fact that it's not instantaneous, this restratification, but it takes a few hours, there is a little alternative that was developed that's called relaxed convective quasi-equilibrium, where you just have the convective tendency that's trying to get your profile back to a reference profile with a typical time span that's fairly short. And so that's, maybe is allowing for a little deviation from those reference profiles and maybe then a little storage of cape, maybe a little inhibition as well. Well, no, the inhibition part, I guess, is something that we have to keep negligible, but that would allow a little bit of storage of instability, that to have just a relaxed convective quasi-equilibrium. In terms of mathematics, it's much easier, right? You just try to get your profile back to the reference profile for the value of humidity and temperature that you have in the boundary layer. So it's probably slightly more physical and a little easier to implement. Now, when you look at observations, convective quasi-equilibrium works pretty well. And it works really well in the core of the convergence zone. So essentially, if you have an intensely convective region, then convective quasi-equilibrium works. When you get to the margins of the convective regions, then it starts to be a little less applicable. And of course, you always have the problem of defining where the margins of those regions are, because you're actually neglecting convective inhibition everywhere. So where is it that you stop convecting? And I'm talking about the margins in terms of in the horizontal dimension, so actual margins of the convective regions, but also the margins of the convective zone in the vertical. If you look at not very intensely convecting regions, there will be an altitude in the upper troposphere at which it starts being less and less a good approximation. So you can think of there is a sort of envelope where it's quite applicable, which has limits both in the horizontal and the vertical. And then on the margins, that's something that doesn't work as well. And there is also that problem that I mentioned about convective inhibition. We know it's not negligible in the subtropics, wherever it's subsiding. We want to neglect it in the deep tropics where it's convecting. How do we do the transition between the two? All right, so the next idea, maybe you can figure it out by yourselves. What's the relationship between this experiment and convection? Any idea? Yeah, that's true. Any other idea? So yeah, it can be advecting more moisture or adding more moisture in some way, maybe through surface fluxes. So the rise can be moisture. Well, it's a little bit like convection upside down. You can imagine that, yes, you're adding moisture from the top. And then what's going to happen is going to fall here on the sides when you get to a level where it gets unstable, right? So we're building up instability by adding moisture. And then you're going to have avalanches of rise. And those avalanches can be like convective events, right? As you can see here, you're going to have avalanches of different sizes, okay? And so this type of process is called self-organized criticality, okay? And so self-organized criticality, you will have different size of avalanches or different size of events. And for that, rice is really good. It really doesn't work as well with sand. And doesn't work as well with cooked rice either. And so this image of convection can work pretty well, and also backed by the data, at least to some extent. If you just plot precipitation as a function of column humidity or column relative humidity, which is what Peters and Dillon did in that paper, you have no precipitation or very little precipitation over a whole range, and then past the threshold, you start having quite a lot of precipitation following a power law. And the variance of the precipitation around that threshold is quite large. And so that's typical of self-organized criticality. So it's a property of dynamical systems that have a critical point as an attractor. So essentially what it means is that your system goes towards that critical point, which is a point at which the physics change. On one side of that point, you'll have certain physics, and other physics. And so when you are in the dry region or in the dry regime, you build up instability. And so sooner or later, you're going to get to the threshold and you're going to start having precipitation. When you have precipitation, you remove instability, so your system is going back to the critical point. So of course, our critical point here, physically, is the transition between shallow and deep convection. And so it's very interesting that it happens for a threshold on humidity. We could think that it would happen on a threshold of convective inhibition, or maybe K, or something, right? So how do we relate column humidity to the different ideas, traditional ideas about convection? Well, there are a few arguments about it. First, of course, there is a role for humidity in the buoyancy. So in the Bombay layer, when you have a lot of humidity, it will contribute to the column humidity, and it will contribute to the buoyancy, so potentially to your updrafts. But when you have humidity in the free troposphere, it will contribute to the development of the updraft, or the non-inhibition of the updraft through entrainment. So in a way, the column relative humidity allows to sum up all those factors into one variable. But it might also be a little bit part of the problems that there is with this idea. So, as I said, we can link these considerations on humidity, or these metrics of the humidity of the column, to the ideas about the dynamics of convection. You can think of it as the way the atmosphere is removing instability following the convective quasi-equilibrium principle. So that's fairly agnostic in terms of the other ideas. There are a few problems, though. This threshold here is actually very difficult to define. It doesn't seem to be universal. And that's probably because there are different factors in this metric. And the different factors, depending on the regions or depending on the temperature, will have different weights. And that makes the precipitable water, or the column relative humidity, not a perfect measure of the contribution of moisture to convection. What you can see here is that in the original paper, they actually rescaled the column humidity, I would say fairly arbitrarily, for it to work well. Now, there was also a paper by Caroline Müller and others that just took a two-layer model with the triggering of convection based on the lower level moisture, so essentially the boundary layer moisture, and then the convective intensity based on the upper layer moisture. So our two different really physical factors that we could make sense of this as a function of sin and k are right there in those two layers in this model. And then she proved that it follows this type of behavior. So you don't need to think of a very fancy idea like self-organized criticality. You can just have it with the two contributions to instability that moisture has at different levels. So, it's still fairly undecided whether it follows a complete self-organized critical process or not. But it's an idea that's sufficiently interesting to be kept in mind. The last one, I don't know how I'm doing with time, but I think we're fine, right? Is the weak temperature gradient approximation. So it comes from the idea that the free tropospheric gradients of buoyancy and temperature are small. And when I say small, it doesn't mean zero. And Vishal authored the work that aimed to show that it's not zero. We have to be careful about really neglecting them completely. But I'm going to take that figure to justify that they are weak anyway. They are weak if you consider the SST. If you compare to the SST, they are significantly smaller. Here you have the SST in the tropics, here you have, so it's the temperature in contours and density temperatures or virtual temperature in shadings at 500 hectopascals. And so you can see that between the warmest regions and the limit of the subtropics around 20, you've got like 6 degrees, right? And if you look at the same in the free troposphere, you have more like 2 degrees, maybe 3. So you're dividing at least by 2 or maybe by 3 the gradients that you have at the surface. And so if you think of a convective quasi-equilibrium, for example, you would expect something that follows more or less the same patterns, right? Because it's tied to the surface. But no, we have something that's weaker. Why is that? Mostly because we'll have redistribution of heat on the horizontal so that we get something that's buoyancy neutral in the free troposphere. That's because we don't have any dissipation. So any energy that you put will force gravity waves that will transport the energy away, essentially. And so that's done mostly by dry gravity waves, and then you can have also a balanced circulation that does that. We've seen with the theory of the Hadley circulation that the circulation flattens the isolines of temperature as well. So I wanted to show a little bit what the dry gravity waves do. Problem with dry gravity waves is that we don't see them most of the time, or if we start seeing them and that they trigger a lot of convection, then they're not dry anymore. There is one marginal case where condensation is kind of passive, and that's this video. And while we watch it, I'll listen to the question. It's a very short video.
So you mentioned dry gravity waves. Do you mean linear dry gravity waves? Because we know convection and linear dry gravity waves will not coexist. Probably you mean moist gravity waves?
No, dry gravity waves. If you have a burst of convection, it will also excite dry modes. They will carry away the part of the energy, a large part actually.
Then you mean probably non-linear part of waves. Because
well, you can have linear wave packets essentially.
Right. I mean, if you have n square as the Brunt-Weiser, then that solution and the convective solution in the dry part is kind of orthogonal, right? I mean, they don't coexist in the linear case.
In the linear case, yeah. I mean, you have also.
You mean non-precipitating but moist, somehow coupled type of gravity waves.
Yeah, I mean. So the ones that are really going to be very fast, they're the dry ones, right? So whether there is some nonlinear effects, it's not quite clear, but what it does is that you have a wave packet that's transporting or flattening the isolines of temperature.
Thanks.
And what you can see in this very short video is that there is a gravity wave that's emitted by convection here. And we can see it only because there is a little bit of condensation at the crest of the wave on the side here. Oops. So you can see it here, right? And so this was also shown in modeling experiment. There is one by Breserton and Smolersky. And you can see that behind the gravity wave packet, you have a much flatter isolines of temperature, isotherms. And so if we can assume that our free tropospheric temperature anomalies are flattened out by dry gravity waves, then we can neglect the anomalies of this temperature. And so that will allow to simplify a few terms in our thermodynamics equation. So I'm showing here the thermodynamic equations with the local change. And if we have our temperature that follows a reference, because it doesn't change on the horizontal, it changes only on the vertical, then we'll be able to neglect both the local change and the horizontal advection. And if we do that, we are left with only two terms, vertical transport and the diabatic heating. And so we'll be able to diagnose the vertical motion as a function of the diabatic heating and our reference profile. And that is quite useful if you want to simplify the dynamics and get the main contribution of dynamics to our physical or diabatic processes, so just the vertical transport. And that's why it was used for parametrizing sometimes the vertical motion in column models. And it works pretty well. So that's why you've heard WTG maybe 3 or 4 times already this week. Well, of course, we have to be at a certain scale that's larger than the mesoscale, essentially. And in theory, it also provides a fairly interesting limit case, as we saw yesterday with the moisture modes. So it filters all the gravity waves, right? Because it neglects the temperature anomaly. And so to isolate moisture modes in a system, they're quite efficient. But that's also one of their problems. We won't be able to have convectively coupled gravity waves with these types of assumptions or simplifications. And it relates to my question to Gilles earlier. It's valid in a free troposphere. Then what happens in the boundary layer, and where can we stop in the boundary layer? And where we stop actually changes things quite a bit. So the idea is that you can assume then that you have maybe vertically homogeneous divergence or convergence in the boundary layer, but then the intensity of that is going to depend on where you decide that the top of the boundary layer is, where you decide that you stop using WTG. And apparently, you know, in Gilles' case, we could actually apply it quite low, like down to the cloud base, the boundary layer cloud base. But that varies to the altitude of the cloud base. The last thing that's interesting with WTG is that you can modify the theory quite a bit, and it provides scalings. So this is a work by Angel Adames from 2022, and you can go to the paper if you're interested in the details because it's not completely trivial. The idea is that you can define horizontal and vertical motions that compensate the diabatic heating completely. So it's a sort of generalized definition of WTG. You could also think of it as a sort of diabatic wind. That's the wind that's really resulting at equilibrium from the diabatic forcing, and you take it to be only divergent so that you can close the system, and you know there's no rotational part to this wind. And then you can look at the wind as a deviation from this WTG or diabatic wind, and that allows you to look at different scales. If you consider that those two, U WTG and U prime, are scaling differently, you can actually start working on the scalings. And if you add just a few more scalings here, you can find 7 different regimes that describe observed tropical convectively coupled motions that are right here, and that are for certain regimes of, so our scalings of the UW, U prime, and our scalings of essentially all other processes. And so there are parameter regimes where you don't really have anything that corresponds to observations. But for each of these regimes, you have a combination of intervals of these scaling parameters that correspond to these regimes. And so you've got equatorial and off-equatorial moisture modes, in which the WTG approximation is very well respected. You have some mixed systems, meaning mixed temperature and moisture systems, for which WTG is still fairly well recognized. So you can still have WTG, and with this scaling, you're still maintaining some variability of the temperature, even if it's small. And then you have the most quasi-geostrophic regime that's also in WTG balance, and then the tropical cyclone, well, tropical depressions that are also in WTG balance, but the tropical cyclones aren't. And the inertial gravity waves are not either, of course. But we can find those scalings for all these phenomena, which is quite interesting. If you think it's interesting, you can go to the article. So, on large scale, we have this influence of convection on dynamics, and conversely, influence on the dynamics on convection. So, how the dynamics work on convection is by changing the profile, and so contributing to convective inhibition or instability, mostly from the latent heating, but also from the radiative effect. Sorry. So the circulation will transport vertically and change the stratification. You can also have some surface flux effects. When you think about the way around from convection to dynamics, then you have the convection that acts by diabatic heating onto the dynamics. And the biggest part of that is the latent heating. And when you look at the equations, those two main effects, latent heating and vertical advection, actually are really the two main terms in the budget. Now, we have a number of ideas to think a little bit systematically about this interaction, which are either really about the interaction or about one of the components. And those are the four that we have seen today. So, convective instability of the second kind, convective quasi-equilibrium, self-organized criticality, and then the weak temperature gradient principle. And that's all. Are there any questions?
Thanks, Gilles. We have time for a few questions.
Yeah, so thank you for the presentation. So what I want to ask is that you just said the self-organized criticality, the entire total column water threshold is not consistent. But I remember like Bretherton 2004, they also mentioned that if you replace that with column integrated relative humidity, the entire like different threshold for different region, that gap gets closed a little bit. But yeah, even though it has its own problem, what I want to ask is, do you think this phenomena is spatially coherent? Because then like Nealon, Holloway, and they were looking into some specific islands over Pacific. But whenever you're looking into a bigger region, let's say in Indian southern monsoon domain, even though you have high total column water vapor, and let's say during monsoon active phase, the entire region is very moist. So you have most of the pixels are actually have more total column water vapor than 50, 55. It doesn't precipitate everywhere. So what I want to ask is, does it mean that there's something also other than self-organized criticality into play when you're looking into the entire spatial coherence of a larger system? So yeah.
Yeah, so I think that there's a problem of validity over land of this. And I think that it depends how of convection is really fueled, essentially. So I think Ole Peters did look at precipitation over Western Europe, and it worked fairly well. But I don't think in any of the analysis they actually included any continental, tropical continental data. And so essentially, I think that what it says is that if the role of your surface fluxes are too important, it's likely to fail. I think if you look, even if you look at small islands, essentially what you see is precipitation that's coming from the ocean that's going to be mostly controlled by the dynamics. And so you're going to have something that's a little bit coherent and consistent. But if you look over Europe, you also have essentially frontal precipitation. So you're going to have precipitation that's controlled by the dynamics as well. So that's going to work a little better, but it's not perfect. Even if you do look at the column relative humidity, there's a little bit of wiggle room right at the point at the critical point, right? So because your data is going to be fairly noisy, it's also a little hard to know exactly where the critical point is, because after that, you can fit your curve. So the theory of self-organized criticality just said that it's going to organize according to a Power law, but the power itself is not specified, right? So you can fit a little bit how you want, and that cannot constrain exactly with this part of the data. You cannot really constrain this point here.
Thank you.
Thank you so much. This was great. I think it's a comment, maybe also a question on your interpretation of convective quasi-equilibrium. So the way I interpret it, I think that I agree with almost all of your statements, but the way I interpret it is that the assumption is not necessarily that CAPE is zero, but that the rate at which CAPE changes is zero, because again, convection being a fast process consumes CAPE as soon as the larger scale, slower processes produce it. So that's my first statement. I think this goes back, or my first kind of comment that I wanted to make. The other thing, and I think we're saying the same thing, but maybe we're interpreting it a little bit differently, is that convective quasi-equilibrium, of course, works well for regions where convection is occurring. And I think the important thing there is that basically the statement is that your coupling changes in the boundary layer moist static energy or moist entropy, where convection is occurring, through your free tropospheric temperature profile. And that, if you also assume weak temperature gradients, of course, already tells you that there are regions in which convection will be suppressed, because of course, only in convective regions you have this coupling between the boundary layer moist static energy content and your free tropospheric temperature profile, whereas in other regions that are not favorable for convection, that coupling doesn't work anymore. And so that is to say that, again, it's not that convective Q is telling you that it's convective everywhere, it's convecting only where moist static energy in the boundary layer maximizes, and that already has some ingredients as to how convection can organize itself, in the sense that where convection happens also suppresses convection elsewhere, because again, where convection is active, you get this coupling. Basically, that is regions of active convection sets the stratification, set the free tropospheric temperature profile that gets communicated to remote regions, and therefore there are regions that cannot meet, that are stable, and so will not convect. So I think that maybe what of course, convective quasi-equilibrium doesn't capture is this transition, for instance, from shallow to deep convection. I agree with that, but again, I wanted to maybe get your opinion on what I just said.
Yeah, so I think, so on the last part, I think we agree perfectly. So I would say that convective quasi-equilibrium, the idea was developed really for deep tropical regions, where it's true that and oceanic regions, where the convective inhibition is relatively small. So yes, the problem is that, and even if you don't like WTG, if you look just at, think of the circulation, we're going to have inhibition in the subtropics or in the dry regions of the tropics. The problem is that when we see that convective quasi-equilibrium is not quite valid in the margins, essentially, we don't know, maybe it's linked to the fact that we don't know where we can where we can start kind of thinking of convection this way or not, because we know we have those two states. Convective inhibition that's quite significant in the subtropics or in the dry regions. Convective inhibition that's probably negligible most of the time over the oceans. Maybe once in a while when you have a perturbation that passes by, maybe you have some inhibition. But because you do see some clear sky over the equatorial Indian Ocean once in a while, right? But in between the two, and since it's exactly where the idea kind of falls apart, we don't have any idea of how to do the junction between the two, right? That's the main problem. To come back about the CAPE, I think the fact that the CAPE is more or less constant comes to the fact that the reference profile is really not quite the moist adiabat, but more of an untraining plume kind of thing. And if you think of it as kind of systematic, then the actual CAPE for that untraining plume, for that reference profile is going to be kind of constant. And so your CAPE is not changing because any instability with respect to that reference profile is going to be eliminated right away. And so your CAPE stays essentially the same. That's how I see it. And I think, yeah, that's probably consistent with what you said.
Strict convective quasi-equilibrium versus a bit more relaxed, I guess.
Yeah, or there's the definition of the reference profile. That's a little bit of a problem. I mean, you can assume some kind of profile of entrainment, and then you have a reference profile, but it might not be very universal.
When we talk about the moisture mode or the moisture mode idea was framed, we talk about the column integrated moisture in general, be it the Bridgerton's case or later in the theoretical thing or the way we do the moisture budget and all. But the thing is, if you look even, in fact, recently, as you also have shown that in the free troposphere is the main region where the moisture is, I mean, and the other thing is under WTG approximation, MSC budget essentially reduces to moisture budget. So in that sense, we think about the column moisture, but most sensitive to the column moisture, I mean, most sensitive relation between convection and column moisture is in the free troposphere. So recently there are many papers by Sobel and Nilin and others which have shown for the moist heat waves. We have a lot of moisture in the boundary layer, and it might be not only just the background, but also it can come from some interseasonal thing. But if you have some sort of inhibition, some sort of inhibition in the free troposphere, even if you have a lot of moisture in the boundary layer, it cannot convect. So in that, but if you take the column moisture idea, you will find a lot of column moisture, but still no precipitation. So in that case, can we think of updating to the moisture mode view to a column integrated, but just integrated in the free troposphere? Will it be a better measurement, or it comes with its own problems?
I don't know, is my main answer. I do think if you just take the free tropospheric moisture, you will also miss some of the effects of the boundary layer moisture on the potential updraft, right? So in a way, you need the two, just like Caroline Müller did in a paper, or when you think about the more traditional vision of convection with CAPE and SIN, you have two variables to control the convection, right? So you have one that allows some storage, and the other who defines what the relaxation is going to be to. Essentially, I think if you average over large regions that are large enough, maybe we can reduce that to one variable, and we can always try that for starters. But I would think that it would not be valid everywhere if you were to develop a model that's only kind of free tropospheric column relative humidity or free tropospheric vertically integrated humidity. You would definitely get the effect on entrainment on convective updrafts, and so maybe over the Western Equatorial Pacific it would be perfect. I don't know about other places. Probably the Eastern Pacific, for example, it wouldn't work, or other continents, tropical continents. I think you would probably run into problems.
Nice presentation, sir.
Thank you.
In my point, in Indian Ocean aspects, like convection circulation coupling indicates tropics and indicates that the lower to mid-tropospheric moisture variations. So in the Eastern Indian Ocean or Bay of Bengal region, nowadays the like mid-tropospheric moisture is decreasing. What are the triggering mechanisms are in the out of 4 theories, which one is most like important or which is suitable for this?
So yeah, let me see if I understand your question correctly. Essentially, you're thinking of during the monsoon over the Bay of Bengal, what would the best theory be? I think on so depends what timescales you're looking at, but if you're looking at maybe synoptic timescales, some aspects would fail. But if you're looking maybe starting at short intraseasonal timescales and above, I would expect the convective quasi-equilibrium to work fairly well because it's a very active region of convections. And I think that for those scales, the interaction with the land masses are not very, very strong.
Okay, sir.
That would be my guess.
Okay. Thank you, sir.
Sir, I have one general way of question only. Global climate model shows weakening of Walker circulation under warming. Yet local convective intensity increases. Can you explain how these contradictory trends could coexist?
Well, I mean, I think the idea of the widening Hadley cell is because we have more intense convection. So you also have effects. You could also have relative effect but in terms of the contribution of the convection, if you have more intense convection, you also have more latent heat release. And so since your radiative cooling is actually fairly limited in how it can vary in the free troposphere in the subtropics, you essentially need a wider area of radiative fins, like in the Pierre-Humbert model, to ensure that the heat budget is closed in the tropics, assuming that the transport to the extratropics is about the same. So that's a lot of assumptions, but yeah, at the same time, you might have a tightening of the ITCZ, so the kind of rich get richer kind of system where you would have the margins that get drier and the core of the ITCZ that gets more intense precipitation. So in that respect, there's also in the intensity of precipitation a factor that's not due to the very large scale energetic constraint, but that's only fairly local. So you have less area of precipitation and more intense precipitation, but you have this factor, but you also have that factor that it's linked to the large scale through essentially the energetic budget.
Small add-up question, sir. How does what you mentioned, this organized convection shows impacts on large scale? How it organized convection affected by large scale circulation?
Sorry, the organized convection or the? You
mentioned convection circulation interaction.
Yeah.
Based on that, how the organized convection existed at a regional scale, how it showing affected by large scale circulation or mesoscale circulations.
Okay, so at the large scale, which is what we're concerned with here, for example, this idea of the self-organized criticality allows us to essentially model precipitation just as a function of humidity. And for example, if you remember Xu Guang's lecture yesterday, that's exactly what he did, right? the precipitation was completely linearly dependent on this humidity variable, which is representing the column integrated. So it was really those ideas that allowed the development of such theoretical models. I think if you were to look at, the climate model, that's a useful tool to understand how it works. But in terms of really trying to use it in terms of understanding of the coupling, that if you have your precipitation that's just a function of moisture, then you can have a direct interaction between the advection and the precipitation. And in a way, just the temperature anomaly is going to be a subproduct of that. So maybe you're going to filter that out or something, but you can just use that in your model.
In the interest of time, let's postpone all the other questions. Let's thank Gilles again for this wonderful lecture.
Thank you.